All right, y'all, good evening. So today we're going to talk about polarity in molecules, and I already have a little bit written out, but this is all just review. Remember, a molecule is any covalently bonded compound. So if we're dealing with any nonmetal and nonmetal, usually we'll get a covalent compound. We'll call that a molecule. Polarity is the separation of charges that result in a dipole moment. And so from here, we're going to take that a step further. A dipole moment being where we have two opposite charges, mostly on opposite sides too. So where this comes into play is we actually first have to come back to our molecules. So what we're going to do is we're going to look at, our bonds. We're going to look at HF. That's what we were starting with before. And F is more electronegative. So F itself is this bond right here is going to have a partial negative and a partial positive, and we would call this a polar bond. But if we look at the molecule as a whole, this side of the molecule is negative, and this side of the hydrogen side is positive-ish, and the fluorine side is negative-ish. And so if I were to go ahead and just draw a line in between, then I'm going to see that one side is negative and one side is positive. So not only is this a polar bond, but because we have a dipole moment across the molecule, so I'll say that we have a dipole moment across the molecule. So we would call this a polar molecule. So it's not too hard to see. And so as I go over polarity in molecules, I'm going to go over two different ways to figure out polarity in a molecule. So two ways to determine polarity. So step one, we're going to use vector notation to determine dipole moment. This is a big fancy way for saying we're going to use arrows to see if there's actually a dipole. And so what that means is usually in any bond like H, F, we can draw a dipole vector. So this is what we call a dipole vector, which shows a dipole moment. It usually goes from the less electronegative to the more electronegative. It points from less electronegative to more electronegative. And one easy way to see that is the more electronegative it is, the more negative it is going to be overall. So over here, we know our fluorine is going to be negative, our hydrogen is going to be positive. And if we look at our dipole, if we just kind of take a brief look at our dipole, over here, the back end looks kind of like a plus sign, like a positive. And the front end looks like a minus sign, the negative. And so that's kind of an easy way to always see it. You can see the little plus right here and the little minus right there. We'll go ahead and fill that in. And that's kind of my easy way to see how we draw these. So if you have a dipole moment, it's polar. So that's kind of what we said right up here. if we have a dipole moment across the molecule, it is a polar molecule. So that's method one. So we're going to try it out on something. So let's go ahead and look at the molecule. So let's do an example. Let's look at the molecule C, F, F, H, H. All right. So in order of electronegativity, H is going to be the lowest, then C, then F. And if you need confirmation, we can always look at our chart. H is 2.2, C is 2.5, and F is 3.98. So I'm actually going to get rid of this because I don't want it right here. We'll just draw a little arrow and we'll say increasing electronegativity. So we're going to go ahead and do the individual dipole for each bond. We will write the dipole vector for each bond. All right. So from hydrogen to carbon, it's going to go from hydrogen to carbon because we go from less electronegative to more electronegative. And I'll go ahead and do that there. Now, from carbon to fluorine, it's going to go from carbon to fluorine because now carbon is less electronegative than fluorine. And when we do this, the way we find out what the net dipole is we add the dipole vectors to check for a net or like total dipole. So I'm going to go ahead and use my fancy program for this. So I'm just going to duplicate that and I'll add all my vectors later. Duplicate. I'm just going to stack them all up. Okay. All right. So I'm going to take these and kind of mess around with them. So when you add dipoles or when you add any vector or any arrows, you just add tail to tip, tail to tip. So I'll go ahead and take this one and put it here. I'll add this one tail to tip. Add this one tail to tip. Add this one tail to tip. So what we see is our net dipole from the tail to the tip looks like that. So I'm going to duplicate this. And we see we have a net dipole moment. Therefore, this is polar. All right, so pretty easy to see how we can figure out whether something is polar or non-polar. So we'll do another quick example of a non-polar molecule. So in our non-polar molecule, we'll do C, H, 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 H. Now, in carbon with 4 hydrogens, each hydrogen, just like that before, is going to have a dipole going towards carbon. However, they're all going to cancel out. This dipole going to the left is going to cancel with that dipole going to the right. This dipole going up is going to cancel with that dipole going down. And if we do our dipole diagram, it's just going to be a box if we add them all. And we're going to start right back where we started, and we're actually going to have no dipole moment. The dipoles cancel out. Therefore, it is non-polar. All right. So the one question that's going to then come up is, well, can I draw it differently to make it seem non-polar? So if we go back to our first example of carbon, hydrogen, fluorine, hydrogen, fluorine. This is the same molecule as before. We have CH2F2, and we still have CH2F2. But in this diagram, it looks like all the arrows are going to cancel out. So is this polar or non-polar? Help me. Well, this is where I can actually show you a little trick. First off, atoms are three-dimensional. When we draw on paper, we get this two-dimensional view of things that's honestly inaccurate. So what I'm going to do is very quickly show you a program. So I'm going to overwrite this screen share. And this program is called MolView. It's a nonprofit that just helps you visualize all chemicals ever pretty much, as well as make your own chemicals, which is really, really cool. So what I did is I drew our two things right here. We have on the left side, carbon with two fluorines on one side and two hydrogens on the other, where we can tell there's going to be a dipole, and carbon with a fluorine on the top and bottom and hydrogen on left and right, which looks like it would cancel. But MolView realizes this is the same compound. If you look at this atom in a different way, so we can rotate it where fluorine is the green one. And if I can rotate this just right, oh gosh, maybe I can't. Almost there. All right, there we go. Right now, it resembles a picture on the left. It resembles the one that we could clearly tell is polar. But with a little bit of tweaking, now it resembles the one on the right, the one that's not polar. So either way, whether the fluorines are on top and bottom and the hydrogens are on the left and right, or if we have it more in this diagram right here, they're both going to be polar because it's the same molecule. It's just now viewed in three dimensions. So that's something to be careful about when working on paper, whether or not our molecules are in three dimensions or two dimensions, and how that affects polarity and the dipole moments. So that's a little bit of a confusing take, but hopefully the second method in determining polarity will help you all out. So let's go ahead and move on to method 2. All right. So method 2, it's going to be pretty basic. If a molecule is symmetrical, it is going to be nonpolar. If a molecule is asymmetrical, meaning not symmetrical, it is going to be polar. And that's it. If there is any way you can look at a molecule and have it be asymmetrical, any way at all, it will be polar. If you can look at a molecule and it's going to be symmetrical in every direction you look, then it is nonpolar. And so we can go ahead and look at our two examples from before. If we look at carbon, fluorine, fluorine, hydrogen, hydrogen, and I go ahead and draw a line through the middle, both sides are different. It is, oh, this is asymmetrical. Therefore, it's going to be polar. You can definitely cut it through a different axis, but that doesn't matter. If there is any possible asymmetrical shape, or asymmetrical, instead of shape, I should use the word division. If there's any way you can divide it where it's any possible asymmetrical axis, so any axis in which it's asymmetrical, it's going to be polar. So I'm going to go ahead and highlight the main point right there. Now, if we look at our other one, methane, CH4, and we go ahead and try and divide it. If I divide it this way, it's symmetrical. This way, it's symmetrical. That way, it's symmetrical. That way, it's symmetrical. This is always symmetrical. Therefore, it is non-polar. So that is the easier way of doing this. If you can see things in 3 dimensions, it really helps out. And we can work on this more. But if it's always symmetrical, it's non-polar. If it's asymmetrical in any way, shape, or form, it's going to be polar. One more good rule of thumb to think about is hydrocarbons. And I drew an arrow from that CH4. So hydrocarbons, so anything made of C and H, pretty much only, will be non-polar. Just general good rule of thumb. So we have CH here, which makes methane, and that's non-polar. However, on this side, C, H, and F, because of that addition of the fluorine, we're going to be polar. And yeah, so that's about it. One more thing to just think about on your way out is if we go COO, CO2. Oxygen is so much more electronegative than carbon. So both are dipoles. Go out towards the oxygen. And this is a symmetrical molecule. So if we divide it in any way, it's going to be non-polar. However, it's a non-polar molecule, but the bonds themselves are polar. So each individual bond is polar, but the overall molecule is not polar. So I'll let you go on that little concept and have a great day.